been here for already 1 week, and I'm enjoying it a lot. And it's my second talk, so let's let's get on with it. What is my question? My question is the following. Take a closed symplectic manifold. Then we have a very big group of Hamiltonian diffeomorphisms. Then it is very interesting to study the topology of this group. So study the topology. In particular, one can study fibrations with structure group, this group. So, one can study the topology of G, but one can also study the topology of the classifying space. Right? So you study which fibrations are not trivial. Right? And as an example, we have the following. Consider our favorite symplectic manifold, closed symplectic manifold. Take CPN, which is, projectivization of Cn plus 1. I'm writing this for a reason. This n plus 1 will come back later many times, and give it the canonical symplectic structure. Fs is for Fubini-Stuti. Okay? Now, Pu n plus 1 is the group of isometries, right? And it embeds into the Hamiltonian group here. So, and I would like to know which kind of topology of Ham is captured by this map. So, right. So, note, by the way. So let's call it maybe iota or something. So for n equal to 1 or 2, this iota is homotopy equivalence. So topology, the same. All right, and in general, we have a number of results. For example, pi 1 of this group, which is a cyclic group of order n plus 1, embeds into pi 1 of this group. And we'd like to know completely somehow whether somehow, from the homotopical point of view, this embeds as a somehow direct summand in here. Okay, so here's a kind of here's a kind of a basic question. Consider the map on classifying spaces that this induces. So BPU n plus 1 into B ham BG. Does this admit homotopy section? Or at least, so maybe this is kind of question 1, which is super strong. So homotopy section would mean that a map like this, such that this composed with this is yes, this composed with this is identity, right? So this is kind of a, I think, a different terminology for this would be a weak retraction. And maybe somehow a consequence of this, but which is still interesting, is consider F over some base with fiber CPN, fibration with structure group, PU n plus 1. Is it still true? And assuming that it is non-trivial, right? As a PUN plus 1 fibration, is it still non-trivial? Still. As Hamiltonian fibration, as Ham CPN fibration. Right. Of course, this is a consequence of this. And what we do is we produce a certain criterion, a partial criterion, for example, for this to hold. So certain non-trivial fibrations extend to non-trivial fibrations, and we can prove it. All right, and let me start by recalling once again. So, what is a Hamiltonian fibration? Right, F over B with fiber M, Hamiltonian fibration. If the structure group reduces to the Hamiltonian group. Okay. And so once again, so example, and even easier than that one, take complex vector bundle, rank n plus 1 complex vector bundle, and just take the projectivization. Right. Okay. So let me say that I include a Hermitian structure here. So it's a Hermitian vector bundle. Okay. So projectivization, example of a Hamiltonian fibration. So this is a Ham fibration. Okay. And the first way of detecting the non-triviality of such Hamiltonian fibrations in general would be to consider certain characteristic classes. So let me quickly recall some characteristic class theory. So this is due to Reznikov and uses results of Guillemin, Lerman, and Sternberg, and I guess and the connection is established in the work of Kedr and Magdav. So what do I want to say? Consider EG over BG as a universal principal G bundle, and then you can always construct from it the universal M bundle. So let me call it F universal, and then there exists really nice class U in the second cohomology of, in fact, of any Hamiltonian fibration. This is kind of what I'm saying here. Universal means any and everything is functorial, right? So there's one like this, such that U restriction to each fiber is the class of omega, and the fiber integral of U to the n plus 1 is 0. So this is called the coupling class. So and Reznikov constructed the following classes. So what's happening here is the following. One can take u to the n plus 1. Well, u to the n plus 1 will integrate to 0, but maybe u to the n plus 1 plus k, well, that will integrate to something, right? So it will integrate to a class in h to k plus 2 of Bg, right? Okay, and then it turns out that these classes, when applied in this case, they allow us to recover the Chern, roughly the Chern classes of the vector bundle. And so from this one, after a certain calculation, one gets that the induced map by this iota this is surjective. Right. So in fact, it's surjective, and the map on oh, sorry, here, there should be an R here. In fact, this is true for instead of R, one can take Q. The dual of this map will be an injection from homology to homology, and that is roughly equivalent to injection on rational homotopy groups. So it's like homotopy groups in a certain stable range. All right, and let me just give you another short example of what would this class U be in here, just to kind of make things fixed. All right, so so if we have let me call this maybe example 0. Sorry. And this will be example 1. So, in notations of example 0, we have the same rank n plus 1 vector bundle. We take projectivization. Then we have the tautological bundle over the projectivization. So this is tautological, right? And then we have the dual tautological bundle. And claim that in this case, wait, let me call this maybe pi. And in this case, U will be C1 of this T plus C1 of pi star E divided by n plus 1. So you see, it's kind of clear that this is not an integral class divided by some things. Okay, and the proof of this is very easy, and it is based on one very nice formula which I want to have on the board. So use this formula. I don't know how to call it. Maybe. So this is formula. This is the formula that Grothendieck uses to define shared classes. So okay, and then this becomes immediate because somehow the only thing relevant for the push forward is this and this. Everything else, restricts to 0 and fibers. Okay. Say again? Yeah, everything else is irrelevant for pi star. Okay, and also another remark that in fact we have slightly more than these classes. We can also have vertical Chern classes. So we have T vertical of our fibration, and then we have C J vertical, which is Cj of T vertical. Okay, and then one can have kind of mu I1 IL K, which is push CI1 vertical, CIL vertical, U to the K. So you have these numbers. So these are also going to be here, and there are some characteristic classes. And in the example, so all of these can be computed through Cj of E tilde and the C1 of T. So take and compute. And then the question is, assume Cj of E tilde vanishes for all j. Can we still do something? Well, clearly not with characteristic classes. Oh, sorry, E tilde is pi star of E. So that's my shorthand for. Okay. All right. So question. Assume Cj of E is 0. Can we show that P of E is non-trivial somehow? And our theorem is yes, we can show. So in certain cases. So take the class of E in K theory. So Octave talked about K theory. This is a slightly different K theory. This is the usual K theory of vector bundles. Well, okay, it's the same K theory. And so take this class. So if this class tensor the class of any line bundle is not a trivial class, so C plus 1. So for all U, just a complex complex line bundle on that, then P of E is non-trivial Hamiltonian fibration. Okay? This is kind of theorem number 1. And here's here's an example. Take. I mean, now I just want an example of a vector bundle, all of whose Chern classes vanish, but but this still holds. And you can cook up such examples, I claim. And let me write 3 lines to show you. I mean, it's roughly the standard such example works. So one can take E0 to be E0 over RP7. And so this is rank 4. Okay, and so yes, you're right. So in fact, I didn't have to write it like this way, but I kind of want to, because somehow this is an important thing. Okay, in fact, let me call this this thing L. I don't know. Okay, and then claim is that this is not stably trivial, but this plus itself is stably trivial. So, okay. So in fact, the reduced K theory in this case is so B is yes, maybe I'll call it B0 is Z mod 8Z, and the generator is L minus 1 minus C. Okay, so then you immediately see. So that's so E0 minus C4 is not 0 in reduced K theory, and twice of this is 0. And this is almost everything, but here I didn't have this line bundle thing. So then you just use a small trick. You say, let E be E0 plus E0 over B, which is B0 cross B0, and then it just works. So using using an easy calculation, that's why it's 4. One can show that all the Cj of E0 are 0, and and then you use Whitney formula, and same is good for the other one. So, and over RP7 there are just 4 line bundles. Z mod 2 cross Z mod 2. RP7 cross RP7. Okay. And then it's easy to check that.
Could that have been 2 instead of 4? If you tensored with C4, could you just have tensored with C2?
No, unfortunately not. Because so I use this formula that this is right. So and then in RP2 this goes to 0, this goes to 0, this goes to 0, because everything is 2 torsion, and Yes, so let me just say that this condition is easily verified. Okay, so here we have a non-trivial RP7 cross RP7 cycle in B ham of CP7 that you cannot detect by these characteristic classes. One might hope that there are some other characteristic classes that detect it, and the first kind of candidate would be my co-author Yasha Savelyev's quantum characteristic classes, which are computed using some kind of family Gromov-Witten invariance. But those actually turn out to vanish for this example too, and roughly for the same reason. So they're kind of defined over Q, and and there's a Whitney formula, and E is torsion in K theory. So I mean,
It's not clear why you couldn't do it over Z.
I agree. Yes. Nevertheless, I think they still vanish. All right, and so this is theorem number one, and let me talk about the methods. And just let me know when I have to stop. Do I have until 20?
Yeah, until 20.
Okay, cool. All right, so let me talk about the method. So our method is related to quantization. And here, by quantization, I mean essentially geometric quantization, but with somehow values in K theory, because we need to kind of take just the first level of quantization, and things become honest vector bundles only for high levels of quantization, so very small h bar. So this is kind of the general words, but now let me make things more precise. So assume that omega is integral, right? So it lies in the image from H2 with integral coefficients into H2 with real coefficients. Then exists L nabla. So this is an Hermitian line bundle equipped with nabla, which is a unitary connection. Such that R of nabla, so the curvature of nabla, well, how to say, normalized by 1 over 2 pi. I kind of ignore 1 over 2 pi everywhere. This is minus I times the symplectic form. This minus is not the standard convention. Usually people say without, but we prefer to do it this way. The only thing we need is to switch the sign in the Hamiltonian construction. So, instead of minus dh, we take dh somewhere. All right, and this is the same as to say that there exists P alpha, where P is a principal S1 bundle. Alpha is a connection 1 form. Okay, and d alpha is minus omega tilde. And omega tilde, once again, is the lift of. So if this is pi, then omega tilde is pi star mu. Right? And this is the minus that is kind of strange, but OK. All right, and by the way, so let's assume just in case that our manifold is simply connected, and then up to isomorphism, this pair is unique. Otherwise, there's some H1 things, H1 ambiguity in the choice of such. H1 with coefficients in S1. All right, so we have this, and then it turns out that in this case, the more natural group is not the Hamiltonian group, but a certain extension of the Hamiltonian group, which is from this geometric data. So this is the quantumorphism group. Let me call it Q. So Q L nabla, which is the same as Q P alpha. So these are just the automorphisms, but but those that don't necessarily restrict to identity on the base. Okay, so in this notation, it's very nice to write. These are all phi diffeomorphisms of P, such that phi star alpha is alpha, and we take identity component. And then this group satisfies the following central extension. So 1 to S1 to Q to Hamilton omega to 1. So if this notation is kind of strange, just think of S1 sitting in C star. Otherwise, it's 0. Okay. All right, and then we have an analogous notion of fibration. Let me erase that. So then we have a notion of pre-quantum fibration. I have no idea why I'm writing in green. Maybe I will switch it to white. So once again, you know, it's a fibration over a base. Fiber is our pre-quantum thing. Structure group is reduced to this Q. But by the way, here we kind of pick this P alpha once and for all. Just pick it. And here's an example. So first of all, if we have CPN and we have the bundle O1 with here we take, you know, the canonical connection, the Chern connection coming from the holomorphic structure and the Hermitian structure, and here we have Fubini-Studi form, then this is a prequantization. And so this is over a point. Right, so over a point. And similarly, if we have a vector bundle like this, then we can take here this tautological bundle and dualize. So it's exactly that T that was there before. Right? Okay, and similarly to the Hamiltonian case, we have UN plus 1 embedding into this Q group in this case. Q of well, O1 number Chern. And in general, somehow the thing to keep in mind that Q to Ham is exactly like UN plus 1 to P UN plus 1. All right. And of course, we have a similar question as in the Hamiltonian case, whether BU n plus 1 mapping to BQ of O1 Nabla canonical, let me call it Qn plus 1, whether this map admits a homotopy section. This admit homotopy sections. All right. So this is about quantization. Somehow about pre-quantization. But now we need to quantize. So let me actually call it Q prime, because it's an analog of Q. All right, so now comes the main kind of tool in this business called the Spincy-Dirac operator. Let me say the following. So we have a prequantization El Nabla of M omega, just like there. And we choose J, to tame almost complex structure. Wait, compatible almost complex structure. And this data canonically assigns us an operator. So which operator? Well, it's going to be elliptic, order 1, self-adjoint operator. And from where to where? So D of maybe L Nabla J from, you just denote it by D, from sections of the 0Q and here let me denote this by some letter. Let me call it, I don't know, like S sub M or something. Now I will tell you what I actually want from this operator, and time permitting, in the end I will actually define it. So the definition is found in a book of Dustermat called Spincy-Dirac operator and something. Actually, it's a heat kernel Lefschetz fixed point theorem for Spincy-Dirac operator. And you can also look in papers of Ma and many papers. Okay, so what do I want from this? Well, first of all, this SM, according to even or odd, splits into two pieces. So it's kind of let me call it S even M S odd M, and then this D looks like this, right? So with respect to this Z2 grading, it's odd operator, and also it's self-adjoint, so it's enough to know one of these two. All right. Now, what I really want is the following proposition, that if m omega j is scalar, and L nabla is a holomorphic Hermitian, and nabla is Chern connection, then d up to some normalization constant, square root of 2 or something, is d bar plus d bar star. Right, so square of this is Laplacian, the d bar Laplacian. Okay, and so as usual, we have an example for for O1 over CPM. So yes, so O1 over P of some vector space, then kernel of D plus is canonically H0 of O1, so which is canonically V star, and co-kernel of D plus, which is isomorphic to kernel of D minus, is 0. So this is a fact of life that I want. All right, and the last thing to do is to write down this thing in families and get our results. So what happens in families? So we have a pre-quantum vibration. So pre-quantum vibration. This gives us a family of operators. So I don't know, let me call it D of B. Well, this family, you see here kind of, I had to choose this J. So here I choose a section, so choose section of what? Of the bundle of spaces of almost complex structures on fibers of F, where F is this Hamiltonian vibration which this underlies. By the way, I forgot to say, every pre-quantum vibration underlies covers a Hamiltonian vibration. It is just because of this formula. Okay, so we have this family of operators. But family of operators, from a family of operators, one can compute the family index, which will be an element in K0. So let's see one way to do this. So we have a map. Sorry. So here I forgot a plus. So I only take the pluses. So we have a map, I don't know, D plus big from two Hilbert bundles, H even to H odd. So these are Sobolev completions. Appropriate Sobolev completions. Right. It's an order 1 operator. One can take a Sobolev with one derivative here and with 0 derivatives here, for example. Okay. So we have this map of a Fredholm map. Fredholm. All of these are Fredholm. Map of Hilbert bundles. So these are Hilbert bundles. And Hilbert bundles can be trivialized, right? So by Kuiper's theorem, there exists homotopy canonical trivializations of H even and odd. Okay, of these Hilbert bundles, and then we get a well-defined class in well-defined homotopy class of maps from B to the space of Fredholm operators on a fixed Hilbert space. So this H here is a fixed, separable, infinite dimensional Hilbert space. So this is the index map. Yes, and it's a well-known theorem of Atiyah and Janich that Fred H is weakly equivalent to Bu cross Z. So, okay, K-theory. All right, and now I'm almost done. I just need to. So there's an invariant of pre-quantum fibrations. Just need to compute it in at least one case, and that would be very nice. So let me call this example 3. So applying example 3 in families sufficiently functorially or on the universal bundles and using, say, Kuiper's theorem 5 more times, at least once, we get the following, that a vector bundle, okay, to it we associate this T over P of E over base, maps by this Dirac invariant to the class of, well, I wanted to say of E, but it's going to be of E star, right? Because there's a star here. So there's a star here, star there. Okay, and moreover, so you see that the K-theory class survives. And it is independent of this choice of almost complex structures because it's a contractible space. So then doing everything kind of I probably just erase. Yes. So here we go. Take the map from BU n+1 to BQ n+1. So this is given by, take duals and extend structured group. I mean, just consider this bundle as this bundle. And this goes, here we have the quantization map to Fredholm of H. And this goes by just the canonical map from BU something to BU. And here I just need to somehow add OL. And there exists a nice weak equivalence such that this homotopically commutes. This homotopically commutes. So you see, we don't quite have a homotopy section, a weak retraction, but something map from this. So, in particular, we can generalize the version of Reznikov's surjectivity theorem, but for Q, so this was done by Aldrich Spacil in Aberdeen. I mean, the Chern-Weil theory generalization. And so we can strengthen it to this classifying space. Okay. And finally, I would like to say something about how we prove the original theorem. Well, that's not too far from here already. So, just need to take care of these line bundles somehow. Well, one does it in one of several ways. One way to do it is to see that this map is equivariant with respect to tensors with line bundles. Another way to show this would be to construct this Dirac invariant, but in a slightly twisted way, corresponding to the fact that not every Hamiltonian fibration is covered by a prequantum fibration. In fact, there's a class in H3 of the base with integral coefficients that measures whether our Hamiltonian fibration can be lifted to a prequantum fibration. And in fact, it's curious. We can show that this class is always torsion using some similar things. So let me just formulate the Hamiltonian statement we can prove. Right. And I guess we will finish that. Okay, so the Hamiltonian statement is slightly stronger than this. So we get for a base B, we get this diagram of K is projectivization composed with E somehow. In B to B ham CPM, and right, so this is somehow a twisted and twisted quantization map. This is somehow comes from W, and that's roughly it. Okay, so this is isomorphism. Wait, sorry, B. So when B is compact, everything is So this is isomorphism, and one can guess the theorem from here. All right. Of course, it would be very interesting. So in this theorem, we look. You see here it's BU, not BPU. So we actually look at bundles with zero obstruction class to lifting. So it would be very interesting to generalize this to non-trivial such classes. And maybe this can be done using the fact that they're always torsion. In fact, their order is at most n plus 1 or 2n plus 2 or something like that. Right, so I think it is time for me to stop, so thank you for your attention.